Welcome back to your Vinta.
And you are here to witness as we sail to the island of
Computing interval estimates of population proportion.
sample proportion. The sample proportion is your best guess for what the true population proportion is given your sample of data.
Confidence level. The confidence level is the probability that the confidence interval contains the true population proportion.
Sample size. This is the total number of samples randomly drawn from your population. The larger the sample size, the more certain you can be that the estimate reflects the population.
Population size. This is the total number of distinct individuals in your population. Furthermore, we will talk about the basic ideas of our given topic.
When we select a random sample from the population of interest, we expect that the sample proportion to be a good estimate of the population proportion. But we also know that sample proportions vary, so we expect some error. Remember, the error here is due to chance. It is not due to a mistake that anyone made.
For a given sample proportion, we will not know the amount of error. So we use the standard error as the estimate we expect in sample proportions. Recall that the standard error is the expected standard deviation of sample proportion when we take many random samples.
If a normal model is a good fit for the sampling distribution, then about 95% of sample proportions estimate the population proportion within these standard errors. We say that we are 95% confident that the following interval contains the population proportion P positive negative margin of error P positive negative 2 multiplied by the standard error, and lastly P positive negative 2 multiplied by the square root of P multiplied by 1 minus P over N.
You may realize that this formula for a confidence interval is a bit odd, since our goal in calculating the confidence interval is to estimate the population proportion P. This is not the usual way statisticians estimate the standard error, but it captured the main idea and allowed us to practice finding and interpreting confidence intervals. Now we develop a different way to estimate standard error that is commonly used in statistical practice. So now let us proceed to the examples.
In a recent poll of 200 households, it was found that 152 households had at least one computer. Estimate the proportion of households in the population that have at least one computer. Now our sample proportion is pretty easy to find. It's just x over n, or 152 over 200, and we find 0.76. That means in our sample, 76% of the households have at least one computer. Now this is just a single estimate. We took, one sample of the entire population, just one sample. So it's probably off from the actual value of the population proportion that we're trying to estimate. Because of this, we're going to create a confidence interval to give a more realistic impression of what the actual population proportion value may be. So first of all, there are two requirements for constructing a meaningful confidence interval about the population proportion, and that is, first of all, the size of your sample has to be no more than 5% the size of the population it came from, and secondly, this weird equation right here. If the sample meets the requirement put forth in this equation, it means that it has approximately a normal distribution, so we can compare it to the normal z distribution using z-tables and stuff like that. So first of all, back to this example, I want you to construct a 95% confidence interval to estimate the population proportion. Now first of all, we have to check if it meets these two requirements. So the first one, yes, 200 households is definitely less than all of the households in the world, definitely 5%, less than 5% of all the households in the world. And second of all, our equation, we find that 36.48 is greater than 10. And don't get too caught up with the meaning of that. Just realize that because it's greater than 10, it means we have approximately a normal distribution, and we can compare it to the normal distribution. So I'm going to take that away, and now we're going to use this equation to calculate the confidence interval. It's still just a point estimate plus or minus a certain margin of error. So here's our equation, and remember we want to calculate a 95% confidence interval. That means we have the 95% in the middle and the 5% left over that's split into those two tails. Now what's split into those two tails, the part that's left over, we're going to refer to as alpha. Alpha is the probability of making a type 1 error, but don't worry about that right now. Just realize that 5% is the part that's left over from our 95%, and it goes into the tails. So like in the equation, you see z alpha divided by 2. Really, that's just saying, okay, z 0.05 divided by 2. That means what is the z-score going to be when there is 0.025 in one of the tails? So and we have this table right here. We go to the z-table, and if there's 0.025 in the tails, that means there's 0.9750 in the body, and that means we're going to use the z-score of 1.96. Hopefully that didn't just confuse you. I've already talked about this a few times, so I don't want to keep going over the same point, but if you look at the lecture on z-scores, it might be a little bit more clear if you didn't understand this, where I got this 1.96 from. So we have this, and we're going to use the 1.96 for our z. So now I'm just going to plug things into the equation. That should be a square root at the top, kind of got cut off. But you can see I put in the 0.76 for the sample proportion. I put in 200 for the size of our sample. And then I put in 1.96 for our z bound. So for our confidence interval, I am 95% confident that the proportion of households in the population with at least one computer is between 0.701 and 0.819.
We finally reach our destination.
We hope you learned something new and enjoyed this video.
Stay tuned for more upcoming adventures.